2 o'clock. Let's get started. First of all, a very warm welcome, and let me take this opportunity to wish you all a very happy new year. This is the first session in 2013, so there are many more sessions that we have planned in the coming months. I'll just walk you through a brief introduction of what we are doing to set the context, and then pass it on to the speakers of the day. So, as you all know, we are. This is the year of Alan Turing's centenary. So, in his honor, we are kind of celebrating this the centenary here. And as part of that, we have been conducting these monthly technology talk sessions, covering various ACM Turing Award recipients and the impact that they have had on the field of computer science in various forms and factors. Each of the speakers has brought in their perspective into their presentations, and that's been a real eye-opener for us to understand, how these pioneers in these their respective fields have contributed and how their work has really impacted and benefited us. As you all know, Alan Turing has been fairly influential in the field of computer science, and that's why he's considered the father of computation. And we want to make sure that, we want to recognize the efforts, the contribution that he has made, and that's why we are celebrating his centenary here. Regarding today's event, it will be in two parts. Today we will be covering the life and work of Dr. Jim Gray, who was the 1988 Turing Award recipient. And the first speaker for today is Dr. Anand Deshpande, the founder, managing director, and CEO of Persistent Systems. Will be followed by a short tea break, and then we'll have the second session. We are really honored to have Professor Trivedi from Duke University, who will talk about some of Jim Gray's contributions in the area of faults, failures, and how one mitigates them. Okay. This event is being broadcast to other locations as well. We have Nagpur there. We have broadcasting to Hyderabad and Goa, our centers in Hyderabad and Goa. We also have a college in Belgaum, the KLE College, who is the students there are listening to us over the voice conference. As I said, this session has been going on since July 2013, 2012, and we'll continue till June 2013 for a year. And since we are seeing a lot of interest, and the audience here is testament to that, we'll most probably continue beyond June 2013 as well, because there's a lot of interest. There's a lot of speakers who have volunteered to speak on different Turing Award recipients. So we'll continue to do that beyond June 2013 as well. Today's session will be on Dr. Jim Gray, followed by next month we'll be having speaker Abhijat Vichare talking about John Bacchus's contribution. Then we have a session by Vijay Raman talking about the contributions made by Ken Thompson and Dennis Ritchie. Then Arvind Benegal will be talking about the work done by Reves Shamir and Edelman, the RSA cryptography algorithms. Then we have Ajay Deshpande will be talking about Barbara Liskov, followed by Hemant Pandey talking about Fran Allen. So these are what we have already planned. These may be change a little bit based on audience interest and availability of speakers and so on. So we may play a little bit around the dates, but roughly this is the tentative schedule. Please do go to the ACM website on which talks about the various Turing Award recipients. There's a lot of information available there. Their papers, the contributions, the videos. It's really a very great site for all of us to go and refresh ourselves on the technology contributions made by these pioneers. As part of this, in addition to the Tech Talk series, we've also been conducting a lot of other events. In August, we conducted a 24-hour programming contest, which was very well. We had a very good participation. We had 18 teams participating from various persistent locations, and the prize money of the winners was donated to various charities as per the wishes of the winning team. We had a technology showcase event in October. We had a a marathon or walkathon run, walkathon based on the Turing theme in December. And the reason we did that was, as many of you may be aware, Alan Turing was a great marathoner as well. So we thought, in his honor, we would have this walkathon/marathon. So I don't think we are in good shape to run a marathon, so walkathon made more sense for us. One forthcoming event is the intercollegiate quiz. So for the students here in the audience, this will be next month. So we'll be reaching out to you to seek your participation in this event. Okay, so keep visiting our website. There's a lot of information available there, and we'll be posting regular updates to that website. And if you have any questions, do send us an email. So this is the ACM a short plug that please do register and join the ACM. It's a good society to be part of. Get to know a lot of technology-oriented papers, access to videos, a lot of material available on the ACM website. So without further ado, let me quickly pass on the mic to Anand Deshpande.
While we get set up, just to check the mic, you can hear me? In other centers as well, if you can't, please alert. One other thing on the ACM India thing, we have a ACM India annual event on the 24th and 25th of January in Chennai. Wind Surf and Sifakis are two speakers who are coming for that event. Any of you want to go there, you're most welcome. I don't think there's a whole lot of entry fee, but you may have to register in advance. So today I'm going to talk a bit about the life and work of Jim Gray. And Jim, of course, did a lot of work in the database area, and I'll share some of the work that he has done. When I sort of said that I would do this, I did not realize how much I would have to work to get this done. And that is predominantly because if you go to Jim Gray's site on Microsoft, the number of papers that he has written and the number of presentations that he has made is phenomenal, and everything is available. So I got really overwhelmed with all the information, and it took me quite a bit of work to get this to a point where I can share something in the next 90 minutes or so. Before I get there, I wanted to share one video just to give you a...
Jim has been called a giant in the fields of database and transaction processing computer systems. He is a member of the National Academy of Engineering, National Academy of Sciences, and the European Academy of Sciences, and is a fellow of the Association for Computing Machinery. He is also the editor of the Morgan Kaufman series in data management systems. In 1998, Jim was awarded the ACM's prestigious AM Turing Award. Before joining Microsoft, Jim worked at Digital Equipment Corporation, Tandem Computers, IBM, and AT&T. He is the editor of the Performance Handbook for Database and Transaction Processing Systems and co-author of Transaction Processing Concepts and Techniques. Jim holds doctorates in computer science from the University of California, Berkeley, the University of Stuttgart, and the University of Paris. Please join me in welcoming Jim Gray. Jim. Thanks for coming.
So this is a pretty nice interview online called Behind the Code. And I'm going to use some snippets from this just to break the monotony of the presentation. So let's get started. So actually, Jim Gray did so much work that when there was a tribute to him in 2008, people asked this question, so why did Jim Gray get the Turing Award for? Because he had done so many things that he could have gotten many Turing Awards on his own. So Mike Stonebreaker, who is actually a very well-known guy in the database area, has a paper on why Jim Gray got the Turing Award. Okay, and this is from the SIGMOD record. And if you look at the citation from his work from the 98 Turing Award, it is predominantly for his work relating to transaction processing. And in the context of transaction processing, he did very seminal work. And I'm going to try to share a little bit about what he did in the context of transaction processing. And a lot of this work, when you're looking at stalwarts like that, you have to look at it from the context of when they did it in the time frame. So I'm going to try to give you the timeline as well as to when this research happened, so that you can relate the context of the machines that they were working with when they did this particular research. So, as was mentioned, Gray did his PhD from Berkeley in 1969 or so. And that's sort of when he was the first computer science PhD from Berkeley. And he joined IBM pretty much straight out. And IBM is where he did his first 10 years. And a lot of work happened along the time that at IBM when he was there. And in 1970, E.F. Cord, designed the relational database. He had this seminal paper in 71. And we had a Turing Award lecture relating to E.F. Cord in the first one when Shyam Nawathe presented this. So he did this work, and relational databases were the in thing in the 70s, and all the early work was going on at IBM. So clearly relational databases are very popular, several $100 billion industry because of the simplicity. And when people were using relational databases, the other things that were going on before were the network model or the hierarchical model for things, and it was all very structured and procedural. So Jim Gray was working with this team trying to do the relational model, and they had declarative queries, ad hoc query languages, algebra for doing mathematical stuff. So it was very query-centric, very simplistic in business models. But one of the challenges that you have when you have a business system you want to build, and banks were the biggest ones, if I'm depositing money in my account and also withdrawing some money, you need to know, what comes first, how do you ensure that they are isolated. I should make sure that my account has the money before I can withdraw it. So there's a whole bunch of transaction stuff that needed to happen. And that's sort of where Jim Gray came in. He defined database transactions and what is today well known as ACID properties. Actually, he is attributed to this, but ACID as a definition came in much later. It came in more in the 87, 88 time frame when he started writing his book with Andreas Reuter. But transactions is something that he worked on. And this is one of his charts where he says that in a database you have reality, which is where you have banks and accounts and money, and the abstraction for that is a database. But when you are doing transactions, one of the things that you do is to maintain a log file where you keep track of all the changes that have happened. And he defined 3 states in which data can be manipulated. Clearly, you can have data which may be in unprotected state, which is the transient state. Then you have data that is protected, and then data that is real. Now, his point was that sometimes when you're looking at databases such as sensors and various other things, the events are going to happen anyway. You cannot control them. So even if you have to roll back, all you can do is to respond to events in case you roll back, but you can't really stop the events from happening. So he separated out the real-time events separately from the protected and unprotected events. And protected events are those which are grouped into transactions and offer a consistent state of transactions. So let me give you a very quick definition of what transactions are all about. So transaction is a sequence of operations that form a single unit of work. So the idea there is that whatever happens between transaction boundaries, begin transaction and end transaction, must be treated as a single unit. Either the entire transaction has to go through or the entire transaction has to be aborted. You cannot do half the job. And this is pretty interesting and important in the following context, that when you are running a system, you have multiple transactions running in parallel. So while there is, we are all familiar that hundreds, thousands of transactions are happening at the same time, many people are accessing bank accounts. And if a particular activity has to happen within a transaction along with many other activities, you have to worry to make sure that you're not going to conflict each other and you're not going to step on each other's toes. So there is a lot of work that needs to happen in terms of ensuring that the transaction is atomic, it can be isolated and run in a durable fashion. And to achieve this transaction setup, one of the things that he proposed was that you need a committed state, and that needs to be accomplished using a single non-volatile storage write. Now that's tricky because when you are running systems, when you write and you have many pages that are still working with half committed data from multiple transactions, how do you ensure that you can write all of it using a single committed write? And if you write somebody else's transaction halfway through, then if you have to undo it, then it can be pretty complicated. So actually this seemed like a pretty simple problem when they started out, but this started out a huge research activity for the last now, since mid-70s till today. A lot of people still continue to work on transaction and transaction semantics. So I'm going to give you a very simplified version of what he did. So essentially what happens is that you define that you have begin work for a particular transaction, you do some work. If you find that for whatever reason you are not able to complete a transaction, then you roll back, meaning abort the transaction, and you go back to the state that was even before the transaction happened. Now if you find everything is fine, you can commit the transaction. Now it can so happen that your transaction may be in an infinite loop and may never end, in which case you need this external system that is going to still go ahead and kill that transaction, because if you can't kill that transaction, you might find that that transaction never ends, and then you have a problem. So rollback can happen by a program calling a rollback or someone else forcing a rollback from outside. So this was his work, and a lot of this happened during his tenure at the IBM San Jose Research Laboratory, where he was working from October 72 to December 1980. All right? And he developed three key ideas. One of them is this whole notion of transaction and the fact that you need to put it like this. And he worked on serializability and consistency related issues. There was a lot of work that he did around locking. And the concept around locking was this fact that if everyone is only reading in the transaction, then it's okay. But if you start writing in the transaction, then you want to make sure that writes happen in a certain order so that you are not in a situation where you can have conflicting writes. So again, main issues here are that you want to have concurrent execution of multiple transactions. If you sequentialize every transaction, then the throughput would be so low that it would not be very interesting. So you need to have multiple transactions running at the same time, and you need to recover despite hardware failure, system failure, environment failure, or whatever else might go wrong. So this whole thing becomes quite challenging, and this is one of the areas that he did a lot of work in. One other thing that he did, which is relating to this whole transaction system, which was pretty unique, was this something that he called the write-ahead log. And in the context of the log, what he suggested was that while the transaction is going to update in place in a database, you keep track of all the activities that you are doing, the changes, in a different file system or a system called the write-ahead log. And in that write-ahead log, you write the old state and the new state every time you want to do it. And whenever you decide a commit, you must do the commit on the write log first rather than doing it on the main database. And when you do a commit on the write log, then you have committed it, it's relatively safe. Then you can choose to write the main pages on your system anytime later, because you know you can always construct it in case you have a problem. Now this was fairly revolutionary at that time and sort of started out the whole concept of relational databases. And this is where he made transactions happen, and I'm going to skip through this. These are the definitions of the 4 ACID things that they talk about: atomicity, consistency, isolation, and durability. And I've already explained some of these things, so I'm not going to go through the details of this. In '93, he wrote a book called, this is a book called Transaction Processing Concepts and Techniques. It's a 1,000-page book. It costs $100 and few. But it's really the Bible for transactions. And he wrote this with Andreas Reuter. And this book is, anybody who wants to work in transactions, must read this book, because this is pretty much where pretty much anything to do with transactions is very well defined. And this book was written in '93. Morgan Kaufman publishes it, and a lot of parts of this are available in online. He runs a workshop very regularly. He used to run one, and slides from that are very easily available. He started, along with a few other colleagues in 1985, a conference that he runs every other year. At least he was running it while he was still around, and now this still continues. I have the link from the last conference, which happened in October 2011. This typically happens in the Bay Area at the Alisumar or one of those kinds of Pacific Heights, Pacific Grove, some of those places along the California coast, typically a 2-day event. And all the top transaction processing people attend this conference called HPTS. Okay, so this has been his contribution again. You will notice that when Gray was doing a lot of his work, he had many collaborators. In every event or every project that he had many collaborators, and many of these collaborators were from different companies as well, and you will see this as you go along. About his early years, so Jim Gray was born on January 12, 1944. And I want to play a short video about how he describes his early years.
So let's go back to you as a child here, try to figure out how you got to where you are today. You were born in San Francisco in 1944, and what is kind of interesting is your first language was Italian, and you spent the first 3 years of your life in the American Embassy. So that's an unusual childhood. You want to tell us how that started?
Yeah, my dad was in the Army, World War II, and he distinguished himself. And when he came out, they gave him a plum job working in the embassy in Rome as an intelligence officer. We had a villa, and his job was to entertain people and figure out who were the good guys and who the bad guys were, and gossip and find out what was going on. And Italy at the time was considering swinging to the very, very far left and becoming seriously communist. And he was trying to forestall that, as were many other people in the U.S. military and the U.S. government.
So, Jim, what did your mother do?
My mother was a school teacher, taught third grade for many, many, many years, and is now retired.
Do you have a sister?
Yeah, my sister Gail was a CPA. She now lives in Mexico.
Well, let's skip to college. You went to the University of California at Berkeley, and you went to school at a time that everybody will remember as the 60s.
Right.
And basically that was the Vietnam War era. It was also, I think, at Cal was the center of the free speech movement.
Right.
And what was it like to go to school there at that really turbulent time?
Well, Berkeley is a great university to this day. It was a great university at the time. Multicultural. Multinational, lots and lots of different ideas. There's a quadrant of the campus which is full of nerds. It's all physics and chemistry and engineering and mathematics and so on. But there are 3 other quadrants that are quite different. I found it to be just a wonderful place to get a good education. The American education system is kind of strange. We screw around till we get to college and then we start learning. It's more or less a socialization process till then, as far as I can tell. And so I had an awful lot of catching up to do. And I had to learn a lot of science and a lot of mathematics, and to learn to read and write, in fact.
I had some problem with my editing, I guess. Okay. So as I mentioned, he also told us that he graduated in '66 from Berkeley as an undergrad. He worked at various places. I want to now move from his first 10 years, as I mentioned, till 1980, he was very much at IBM, did very productive work. The rest of the group was pretty well known. They were the guys who did all the system R work, and the kinds of papers that got written up and the work that was done is quite phenomenal. He moved kind of unusually at that time to a very small company called Tandem in 1980. It was about 2,000 people, and he just kind of felt like moving, and he was looking at something new to do, and he wanted to be in a small place, and he went to Tandem and actually implemented a lot of the code that he was doing research about at IBM in the Tandem Nonstop SQL is what their product was called. One of his very well-known, of course he's written a lot of papers around that time, but I'm going to skip that and take you fast forward to 1987, which is actually a very interesting piece of work that he did while he was at Tandem. And this is called the 5-minute rule. So his concept at that time was that, okay, you have pages in main memory, RAM, and then you have the disk. There's a cost of getting to the disk, but when you get to the disk, you can pull in a large chunk, such as a page, and you can keep it in main memory. Now, if you keep it in main memory, the more you keep in main memory, yes, it's easy to access, it's quicker to get to it, but it's expensive to buy main memory. So his question was, at what point does it make sense to keep something in main memory rather than leave it in the disk. Okay, so if I'm going to need the same thing again and again all the time, I should keep it in main memory. And if I don't need it often enough, I should put it in disk. But what is that golden mean? What time can you calculate some of the work that you can do in terms of the empirical number of what is a good number, when you should leave it in main memory and when should you put it in the disk? And then he came up with this argument that I don't want to go through, but I just want to leave these numbers here for the sense of what the price points of various equipment was at that time. So, he's talking about tandem, 15 accesses per second, priced at $15,000 for a small disk or $20,000 for a small disk. And price per access per second is $1,000, CPU, all that other stuff. And then he calculates various things to come to a 5-minute rule. And his point at that time to note is that you are looking at 1 kilobyte pages. So if I had something in a 1 kilobyte page that I was going to touch within the 5 minutes, then it made sense to leave it in main memory rather than putting it into the disk or letting it go away. And this helped a lot in trying to decide how much main memory should you buy and a lot of this stuff. Now, if you look at a lot of Jim Gray's work, he was very empirical in a whole bunch of work that he did. Now, this is something he did in 1987 when he was at Tandem. And this equation that he comes up with is basically what it says is that you have pages per megabyte of RAM divided by access per second per disk, and then price per disk. And so here are two terms here. One of them on the left is the technology ratio, and the other one is the economic ratio. And by multiplying the two, you can find out the break-even point in terms of how many seconds it should be. Now, this particular thing he reviewed again in 1997, this time with Getz graph. He was at Microsoft at that time. And this is a paper that he wrote in 97. And there again, he did some more additions, modified the formulas a bit, suggested a few more terms. So he talks a lot about how long it would take to scan the disk. So what he found is that while some of the other things that improved, that kilobytes per object served per second, how many megabytes objects per serve, multi-scan, and all those kinds of things, the basic disk scan was still pretty slow. And he came up with some of these facts that, when he did the experiment in 87, he was talking about $20,000 for a disk. This came down to $1,000, and disks got cheaper, data got cooler, and all of those kinds of things. And essentially, you got into these kinds of numbers there. And I don't want to go through these numbers here today, but let me just move into. And then he did these charts on how disk, cache, memory, secondary memory, disk tape, all those things on the left-hand side with size and speed, and then price and speed, to try to get a sense on what is the right kind of numbers on this. And in summary, he said that the 5-minute rule still holds in 1997, but the page size now, instead of being 1K, is 8K. Okay, so now 8 kilobytes of per page, if you do that, then if you use that in your calculation, the 5-minute rule still holds good. And this was some of the analysis that he did with data where he was looking at disk prices and some of the data from 97. And he talked quite a bit about it. He updated it in 2000, 2002, and so on. And this is one of the presentations that I've seen him do, and I wanted to share this from his presentation. This is actually a very interesting way of how he used to present. So what he says is that how far are things? So he said, okay, if let's say going to the register is like a nanosecond, one unit, then going to the chip, which is on the cache, is typically like 2 units. On the board, it's 10 units. So whatever the clock frequency may be. When you go to the memory, it's about 100. When you go to the disk, it's 10 to the power 6. And when you go to the tape, it's 10 to the power 9. And his concept was that if I just map this to real things, what does 10 to the power 6 mean? And what does 10 to the power 9 mean? So he said that, okay, if it's 1 unit, it's like getting it from my brain. So I ask you a question, who is so-and-so, and I can give you an answer. 1 second, I can give it back. Or within a minute, I can give you back some information that I have in my brain. Now, if I have to go to an on-chip register, it's like walking to somebody in the other side of the room and asking, hey, can you tell me what this is, and you tell me back. So within 8-10 minutes, you can get that information within that building. If I have to go to memory, it's like getting it in an hour and a half. So maybe I have to drive to the other part of the city and come back. So 1.5 hours, you can get it. Now, if I have to go to disk, it's like taking 2 years. It's like going to Pluto and coming back. And if I have to go to a tape, it's like 2,000 years. So essentially, you take the same kind of numbers, 10 to the power 3, 10 to the power 6, and try to multiply them in real numbers. And you see that if I have to get something from main memory, it's like, or from my CPU registers, it's like getting it from my brain within a few seconds, within a minute I get it. An order of magnitude on that, if I have to go to the tape, is like going to Andromeda, or if I have to get it from a disk, it's like getting it from it's going to take me 2 years to get it. So this is sort of how he compared this, and all of a sudden now when you look at the numbers on the right hand side, when I tell you 10 to the power 6 and 10 to the power 9 nanoseconds or whatever else, it just doesn't make as much sense as it makes when you sort of compare it when saying, okay, when you have to go to Andromeda, it's really far away. So tapes are so far away that if I can get something closer to my system, then all the better I can get to be far more efficient. This is another thing that he presented in '95, where he sort of said, what is a terabyte? At that time, terabyte was a very big number. Yeah, this is '95. People were talking about megabytes on disks, and some high-end things had gigabytes, but it was pretty small. So he said, what is a terabyte? So he had this in his presentation. So he said, it's like 150 miles of bookshelves, 15 miles of bookshelves if I keep book pages. If I type the text and keep text, then it's so many business letters, which is 150 miles of bookshelf. If I scan them, fax images, if I put TV images, if I put web pages or Landsat images, it's like 10 Earth images or whatever. So what is 1 terabyte? And then he said that the Library of Congress is only 25 terabytes. And in 1980 prices, it's, on tapes, what is the cost, on files, what is the cost. So he was very empirical in a lot of his research in trying to figure out what is the cost, the size, and then comparing them with real facts, because that sort of made it much more interesting, which is where his presentation skills and all the stuff that he talked about, and his ability to simplify things for people who may not all be, terabyte sort of seems like, okay, what is a terabyte? You have no idea what it is, but when you explain it like this, he does it really well. He had another equation which he talked about on what is cheaper, is paper cheaper, or when is disk cheaper than paper, and all of those kinds of equations that he had a lot of those things in his presentations at that time. Another thing that this is again from his slides around that time, where he talks about, again, what is a terabyte. So he says, all right, a book is a kilobyte roughly, a photograph is a megabyte, gigabyte would be in the movies range, all of Library of Congress books, a few terabytes, all the books and multimedia would be a few petabytes, and everything recorded maybe zettabytes or whatever. And then he said that, again, this is very perceptive. He said that everything can be seen and recorded can pretty much be on the disk pretty soon. And he's talking in '95, okay, so '94, '95, before Google, before all the internet happened. And he said one of the challenges is going to be getting human attention. So auto-summarization, auto-search keys, those are going to be much harder problems to solve, not so much the ability to collect and keep the information. So again, this particular 5-minute rule kept coming back. In 2007, Getz Graph, now at HP, published this, relooked at the same 5-minute rule and did the same analysis. But essentially what he came back with is saying that 5-minute rule still works, but now the page size is 64 kilobytes. We were 1K, 8K, it went to 64K. But then he also said that, now we have flash memory, which actually is something that goes between the disk and the RAM, and something that you need to consider and look at flash memory as something intermediate. And then he came up with some more corollaries to rules in terms of how do you move stuff from flash to RAM and RAM to flash to disk. So now he had 3 levels of hierarchy, and he does a lot of work on this particular one. Very nicely written paper. It's, again, all of this stuff is available online quite easily. This is from the ACMQ, which is where this one is available. Again, this has not ended. There's this article that came out from May 2010, where they talk again about the 5-minute rule. More recently, this is from, this is by 24th August. This is by Werner Vogels from Amazon and AWS. He's talking about they're making what is the storage on the cloud, what would that price point look like. So again, he says, comparing back to the 87, 97, 2007, now 2012, now with the cloud, what does this 5-minute rule look like? So this particular work of his has sort of continued over and over again, and he has been getting attributed to this work all over the time, and this has been used quite a bit. Okay, so if you have any questions, of course, please stop me, but I'm essentially talking at a fairly sort of high level rather than any depth here because of the breadth of the work that he has done. One other piece of work that I wanted to share with you was from the 96, 97 time frame. This is the work that he did around what is known as data cube. And in the data cube context, again, here amongst all the authors, he has Hamid Piraish, who is from IBM Research. The rest of the guys are all from Microsoft. And the concept here is that, pretty much till then, SQL standard, which was designed became popular in 92, had this aggregate operators, and there were 5 of them: count, sum, min, max, and average. That's it. And essentially what happens in an aggregate is that you aggregate it, you get one value back for that total. So you do this select, distinct, average, or whatever from a certain table, and you get back one value. Now you can do slightly better by getting more sort of distribution by doing a group by, where you can group on a certain attribute and collect aggregates on some other attributes, and that gives you a table back which has certain things. But essentially, relational databases and databases of this kind, and SQL in particular, were really poorly designed for aggregates and pretty much analytics that was happening. Now this is 95, 96. So he found that people want histograms, you want subtotals, you want crosstabs. Versions of Excel had come in with a crosstab or a pivot table, as they called it, and they realized that they needed better sophistication than just the group by. So he came up, and then other companies had other variants, such as Illustra had a variant called, they had something called Data Blades, in which you could create your own user-defined aggregates. And essentially they said you can create something where you define the init function, the first function, the final function, and then the iterator. And as long as you have an iterator, you can run through the values and create aggregates. So what he did was he said he defined a function called data cube, where he said that in the group by, I should be able to create a cube between multiple attributes, such as model, year, and value, or color here. And then you can create a multi-dimensional table here. And this is sort of was the time and the beginning of the OLAP industry in some sense. So till this point, data warehousing and OLAP was not necessarily anything that people cared about. Most of the database was all about transactions and OLTP. 95, 96, people started to talk about warehousing, aggregates, and OLAP. And one of the fundamental things that you need for an OLAP is the ability to create cubes. And this is sort of where this whole thing started. This was 97, 98. And then a large number of companies happened around BI and analytics. Okay, so 98 is when he got the Turing Award. And this is from there. And normally what happens for the people who get a Turing Award is that the Turing Award is actually given towards the end of the year. So 98 November is when he received the 1998 Turing Award. He would have actually gotten that award at a function in May sometime, when there's a formal function and they give the award. And at that time, the award was 25,000 rupees. Now it's about $250,000. So ACM Award, Turing Award is like the Nobel Prize in computer science, and is the most prestigious award for computer scientists. And he got this in '98. And after you get that award, the person who gets it gives a presentation, which is typically called the Turing lecture. And that Turing lecture is where he talks about his past and future work and whatever else. So Jim Gray gave this Turing lecture in '99, where he talks about what's next, a dozen information technology research goals. And he talks a lot about this. For example, the scalability problem has motivated me for several decades. And he gave a list of 12 problems that he thought are research goals for information technology, and he left them. And I'm going to share those goals with you as just a list of those things. So one, of course, was he was very big into scalability, saying, okay, how do you build systems, hardware, software, which can scale up and down? So he had this whole thing about how do you do speed up and scale up. And I'll talk a little bit about this because this was some of the works that he continued to do after '97, '98 when he got the Turing Award. Now the Turing test, I don't know how many of you are familiar with what the Turing test is, but the Turing test is something where Alan Turing made this test, saying that he said that in 50 years, computers will be able to pretend to be human beings in a sense. So you will not be able to distinguish when you are talking to somebody whether the other side is a machine or a person. And around '97, he says that 30% of the time, the computer system wins, that you can, and 70% of the time you are able to make out that it's a computer and not really a human being. So his point was that we need to build a system where you can imitate the human being all the time or most of the time. And then he talks about speech to text, text to speech, can you see as well as the person? A lot of these things have not happened, but if you looked at some of the predictions from IBM this year, they talk about smell and all the 5 senses that they can get in the next 5 years. So a lot of progress has happened in the last couple of years in these areas. Then he talked about something called personal memex. This is from the work that was done by Vannevar Bush. So he said in 1945 about this whole thing about how do you record information and all that stuff. And he says that in a personal memex, record everything a person sees and hears and quickly retrieve any information on request. World memex built a system that pretty much does the same thing across the whole world, and whatever else can be done on that. And again, he continued to work on these 2 problems, and I'll share with you a little bit about what he did there. Telepresence, again, was something he talked about. Trouble-free systems, secure system, and always up, where these are other things that he mentioned. And finally, he talked about an automatic programmer. So these were the 12 problems he sort of shared. And just to make some of these more complicated, just in case somebody were able to solve it, he added these kinds of things to the end, saying that, and prove it, okay? So that means another 15, 20 years you can keep working on it. So again, as I pointed out, he had this whole knack of numbers, metrics, and trying to measure things and all that stuff. So he talks a lot about these thumb rules that he has in the computer industry. I don't want to go through these, but these are very interesting laws that you can take a look at online. Metcalfe's law, Moore's law, you're familiar with. And then he has some others. And then he had, because of where we are today, he talks a lot about this Gordon Bell's 7 price tiers. $10 wristwatch computers, Palm computers, and all that stuff. See, they don't have the cell phone in this at that time. Cell phone was not really seen as a computer or anything to do with smartphones and computers. But they were talking about wristwatch computers to be in tens of dollars. Kind of almost there with the cell phone being not only a wristwatch but can do many more things. And then you can get these smartphones for hundreds of dollars. Portable computers, of course, now look very different from what he may have said in '95, '96. Okay, now this is another one of those things. So when he moved to from digital to Microsoft, Bill Gates has this whole thing called information at your fingertips, and that was their main logo. And he was known for his long-standing belief that everything should be put into, every information should be available on your fingertips. And he started to champion this all as early as 1989. And this is one of his visions, that he talks about global data federation, saying massive data sets live near their owners. And I want to skip through this because I'm running a little behind, but I'll come back to what he means here. And so again, this is around the time when he did a lot of work with another very well-known computer scientist called Gordon Bell. Gordon Bell used to be at Digital with him and then moved to Microsoft together, and they worked together quite a bit. And two projects that they worked a lot on, which have influenced his work at a later point, from the mid-90s on. This is all the work that he did at Microsoft. One of them is called My Life Bits. And what Gordon Bell did was he started to say that, this personal memex over, he started to essentially say that I'm going to collect everything that I've seen, written, read, and collect it all in a digital way, and everything I do will be digitally recorded, and all. Anything I see, anything I hear, what would that look like, and can I search through my life, kind of stuff. So he's been doing this for, I guess, several years. And he wrote a book called Total Recall, okay? And then he got this into a website and some other thing going on called Your Life Uploaded. Okay, and this book is available on Amazon, and of course you can take a look at it. And then, so this was one stream of work. This group continues to work on this problem, and they do certain things there. And then this was a TerraServer project. And again, I want to share a little bit about how this TerraServer happened, because it has some interesting implications on where it goes. And if you look at the context in which he did this TerraServer, actually it's pretty interesting. So this happened in '96. And for those of you who are not aware, actually Microsoft did not have databases before '95, '96. They had no database at all. They were predominantly Windows was their main product. They had Visual Basic, Visual Studio, those kinds of products. Then they got into Office, and they had Word, Excel. Then they made Office out of that. They did not have a database. They actually bought something from Sybase and then kind of rehashed it and made SQL Server out of it. And at that time, they went and hired a lot of people who never thought Microsoft would be a database company. And then they built a group from scratch for this whole thing that is today called SQL Server. And Gray was working on that. And one of the problems that Microsoft always had was Microsoft was always seen as a client-oriented company. They wanted to get NT, which was their new product that they had, the Windows NT product in early 90s, to be a server-side product, not just a client-side product. And for them to have any credibility in the server-side market, they needed to have some server-side products like a database. And that sort of forced them to say that, okay, we need to create this, we need to have Windows NT, we need to have Windows NT run our database, and that should run SQL Server. And they went and acquired a code base from Sybase and completely rewrote it after that. So that's sort of the history of what happened. And Gray joined in at the research lab, very well-known guy in databases, having done phenomenal amount of work at IBM, then again run non-stop SQL at Tandem, were very well-known there. Digital, he had done some phenomenal work. But again, he was not the guy who was going to write code. But then he sort of was halfway between research and product and was talking to all kinds of customers. So essentially what happened was their boss out there, Paul Flessner, told Gray that, hey, I'll give you machines, I'll give you hardware, build something big on SQL Server that you can show to the world, right? So that everybody can see that I have something that can be used. So he built this thing called the TerraServer project. And the idea there was, let me skip this, I'll come back to that. So he created these kinds of requirements for the TerraServer. Again, we are in the pre-terabyte. Terabyte was a big thing in '95. People knew that we will get to it, but they had not seen it. Okay, so terabyte of data was a big thing, catalog, temporary space, public, anybody can use it. Web had started to happen, accessible everywhere. Should be interesting to a wide audience, real, free, easy. So basically like a data repository that you can use, data as a service, okay, without calling it that. Now, who was going to give him data at that time? So he went to people like the US Geological Survey. He went to the various mapping places, aerial images from Soviet satellites, and a bunch of things, and created a system based out of SQL Server, storing images in SQL Server and all of that stuff, and created this product which was called the TerraServer. In June '98, they had a big team and they released this product, but this actually gave them a lot of credibility and a lot of interest in trying to work on that. And while he was working on the TerraServer, he started to work a lot on this scalable servers business. And again, whenever Jim Gray did something, he wrote a lot of stuff. He went around the community explaining to people what he was thinking, and he was kind of doing open source research in some sense. And he talked a lot about scale up, scale out, and scale down. So his idea was that, yeah, you want to get a TerraServer. What can you do? One is you can make your SMP processor be bigger and bigger, put more memory, put more disk, and make one big Cray type machine. So that's one way to do it. And the other one is you can go create a cluster of things. So what happens when you create the cluster? SMP, of course, you have the advantage that you're running one image across the big processor, and it works out quite well. And you can keep doing it for a point. How big can you get? You have to go to the factory to put a bigger and bigger machine all the time. And then he came up with this thing that, okay, is it possible to create a cluster? And one of the challenges that at Microsoft they were looking at was this whole concept of 1 billion transactions per day. Okay? And how can you have a machine and SQL Server database all to run 1 billion transactions per day? So that was the objective of what they were trying to do. 1 terabyte database and 1 billion transactions. And he sort of started to propagate a lot about how to build these clusters. And his point was, can you take clients and servers from inexpensive commodity components and build out a cluster which is modular and can be put together in a way such that you get many of these put together, and if you needed more, you can keep adding more and more. And he built these using Windows NT, of course, being part of Microsoft. And he thought a lot about parallelism in the context of clustered programming. And I'm trying to bring this up here predominantly because if you see what happened in the industry beyond what Gray did, some of the work that happened at Google and Yahoo and all of those, you could very clearly see that what he was talking in 95, 96 actually went into production at Google and Yahoo and all the way across through that. And he talks a lot about pipeline parallelism, partition parallelism, saying that how do I take a job and actually partition it so that it can run on multiple different clustered images at the same time. And he had something which he talks a lot about at that time called data reverse, where you say, okay, how do I split the data and then merge them eventually? Now this is sort of, later on if you look at this today, you might seem like somewhat like MapReduce here. But this is sort of the early days. He's talking about this in 97, 98. And he talks a lot about data partitioning, split, merge, and these exchange operators and all that stuff, these are all within Volcano, which was the SQL Server version that they were using. So I'm going to skip through this very quickly, but what he was talking in 96, 97 was that he predicted that in 2000 you will have a 4B machine, okay, which would be commodity. His 4B machine was that it will run billion instructions per second, it will have 100 megabytes of RAM, 1 billion bits per second of network, 10 billion bytes of disk, meaning 10 gigabytes of disk, billion pixel display. Okay, and it would cost $1,000. This was his 4B machine, and then he created this thing called the 4T machine, which is his super server, and he called these stuff cyber bricks. So his point was, how do I create these small commodity hardware machines, take them, stick them one after the other, and build a huge machine that you can keep adding bricks to it, and as you add more and more bricks, you can get more and more hardware. And how do you deal with manageability, scalability, programmability of these kinds of machines? So this was sort of his main theme that he was working on. Now when he was looking at building these kinds of machines, he said, well, I have all these machines, but how do I what do I do with them? So I need some big problems to solve using this. And he at that time connected with this gentleman called Alex Zale, who is an astronomer from Johns Hopkins. Actually, he has come here before. We've worked with him at Persistent. And he's an amazing guy. He comes to Ayuka quite regularly. And he has been working on something called the SkyServer. And I wanted to share a little bit of a video here about some of the, why does he talk about this? Okay, there was another one he talked about called...
You did an invited ACM paper, and you used an analogy that I think we...
So again, when he was trying to build these kinds of big machines and all that, he was always well known for these analogies. And this is a one that people use a lot about called the smoking hairy golf ball. So I don't know if you've heard about what the smoking hairy golf ball is. And he wrote an ACM paper, which was an invited paper about the smoking hairy golf ball. And he explains that smoking hairy golf ball in this video clip here.
Smoking hairy golf balls.
Right.
We have a smoking hairy
Yeah, absolutely.
golf
I
ball.
brought mine along. Yeah. So here it is. So, and the concept is that the speed of light is finite, and a nanosecond is a foot. Okay? And so if you buy a gigahertz processor, it's doing something every nanosecond. Okay, so that's the event horizon, but that's in a vacuum. The processor is not a vacuum. And signals don't go in a straight line. And the processor is running at 3 gigahertz. So you don't have a foot, you've got 4 inches. And the speed of light is in a solid is less than that. So you've got, this is the event horizon. If something happens on one side of this thing, the clock is going to tick before the signal gets to the other side. Okay? So that's why processors of the future have to be small. Okay? And in fact, golf ball size. Okay? Why are they smoking? Well, because they have to run on a lot of electricity. The way you get things to go fast is you put a lot of power into them. And so heat dissipation is a big problem. Now, it's astonishing to me that Intel has decided that this is a big problem only recently, because people knew that we were headed towards this heat cliff a long time ago. And why is it hairy? Because you've got to get signals in and out of it. So this thing is going to be wrapped in pins. Now, another interesting thing about this is that we actually haven't gone 3D with our processor architectures. The processor architectures are, some integer number of layers, like 10 or 20. But we could actually make 3D things which would give us much better space density if we could deal with the heat problem. So probably in the next decade, the processors will be sort of on this scale, and cooling is going to be the big problem for them.
Well, before we move on, I'd like to ask you a question about your role is part of a larger initiative called eScience.
Right.
So can you tell us about that?
Sure. So one of the reasons I came to Microsoft is that our so-called strategic intent is information at your fingertips. And what that means for knowledge workers in the future is vast amounts of information that they, in fact, are struggling to understand. I mean, it's not that the problem is that the information isn't at your fingertips. It's just that there's, petabytes of it out there. How the heck do you get to it? And one context in which you can explore that is the area of sciences. So the scientific community is gathering information at a prodigious rate. And unlike the situation at Walmart or the situation in many commercial enterprises, the science community is pretty public about what they're doing. So if we work with, say, Target or Walmart, we can't talk to the other about what we're doing with them. If we work with the science community, we can talk to people and other physicists about what these physicists are doing, or in fact, biologists about what the physicists are doing. So I've taken the task of getting all of the science data online, getting it accessible so that you can easily understand what the information means, getting it cross-indexed to the literature, getting it cross-indexed to the other sciences, as being a really good challenge for Microsoft as part of information at the fingertips.
What's the hardest part of SkyServer?
Well, SkyServer is the astronomers first. Somebody explained to me once that computing would be really easy if it weren't for tapes and users. And so the biggest problem with the SkyServer is the astronomers. Okay? that it's very, very hard to get people to agree. And that the fundamental thing we're trying to do with the SkyServer is build a conceptual model for astronomy. And that means that you have to agree on what a star is. And you have to agree on what a galaxy is. And you have to agree where the galaxy starts and stops. And you have to agree on how you're going to measure things.
Okay, so he was pretty much, so if you see he has always had this empirical bent of mind, and he was always working on these things. Mid-90s, he got involved in this TerraServer. He built this out 2000, looking at petabytes and all that stuff, and he's looking for problems to solve. And then he meets this guy, Alex, who has been an astronomer. And then he got into this whole area for the next, till at the end of his life. He pretty much dedicated his life to data, computing, and science. And there's a lot that got written out in what is known as the fourth paradigm. I'm going to just quickly explain to you what he means by fourth paradigm. So to explain that, you need to know what's the first paradigm. And in his context, the first paradigm is stuff that Galileo and other people did for thousands of years. It was all about empirically describing natural phenomena. So you looked at what was available, or you looked at the stars, and you observed it, and you wrote it down, and that was science. So it was more observation driven. In the second paradigm, which is sort of the Newton and Maxwell, Kepler, all these guys, they not only observed what was there, but they also postulated theories around that. So they said there are the Newton's laws, or laws of Kepler or Maxwell's equations. All these things happened. And their point was that they were not only observing, but they were defining laws. And now they could interpolate or come up with other things and theories that met the law, even though they did not have other observations. And in the future, a lot of experiments were conducted because they knew the law and they were expecting certain behavior, and they could always validate or not validate those laws or things like that. So this is what he termed as the second paradigm. The third paradigm was more about simulation. So he's saying that, okay, we're going to use the computers and computer modeling to simulate large problems. So we don't know exactly what the equations are. They are too complex, but we are going to go and simulate them. And if the simulation results meet what we are looking for, then our assumptions must be correct. And that's how a lot of the science happened in the 25 years, last 30, 40 years that computers have become pretty prominent. What he talked about is this whole thing called the fourth paradigm, which is data-intensive science. And in this, what he said is that in the scientific methods traditionally, anytime you did an experiment, you were doing a hypothesis first and you were validating it using an experiment. So you had a hypothesis that I'm expecting certain behavior, and you define an experiment to meet or validate that hypothesis. However, in a data-driven approach, researchers just start collecting data and analyze it later. So what they are trying to do here is that they start collecting data from experiments, instruments, simulation, literature, and other archives. And once you have all the data, then you ask questions to the database to say, okay, hey, I'm expecting this. Is this true or not? And this happened, this is actually how astronomers have been working for the last 10 years or so. So they have this thing called SkyServer. So, again, we've been working here with the local astronomers. So I can share some of the stories that they have shared with us. So essentially what happens in astronomy is that they have these big telescopes. Big telescopes are really big, and you have to put a time for it, and you've got to book it several months in advance. And if it's one of those optical telescopes, you go there, and your observation is blocked because you had a cloudy day, and then you're screwed for several years. But in any case, if you are able to get a reading, then your PhD thesis pretty much is all about creating some theory, identifying what you want to do, getting time in an observatory in maybe Peru or Chile or whatever, go there for a week or a month, sit down, collect all the observations you can, come back and then do Perl scripts and analyze your data for the next 3 years, and then whatever you get, if you're lucky, is your PhD, and otherwise try again. So unfortunately, this is how they have been doing this research. And what happened through this SDSS project, which was a SkyServer, what they said is that, well, let's just let these surveys continuously collect what is there in the sky. It doesn't matter what it is. Let's just keep observing all the time continuously. We'll keep scanning the sky, and just collect all that data on the disk. So I don't need to go to the observatory at all, and I can just look at it up all the time and then look to the database rather than going to a telescope. So I don't have to give you the telescope. The telescope is continuously scanning. Now, many people offered their telescopes. So some are optical, some are, infrared. We have a radio telescope here in Pune. All these telescopes collect all this data. And they started to put this out into what is known as the virtual observatory. And they said, okay, let's put all the data from various telescopes all over together, and let's use good computation and data science to figure out when I'm looking at a particular section of the sky, how do I want to do it? So astronomy today can be about going to a computer screen, defining the segment in the sky you want to see, and then you can get observations as they have come from the Hubble telescope. You can go to the Hawaii telescope, the Chilean telescope, wherever else, some infrared, some all of those, and then compare them and do science according to that. And actually, I want to spend some time on this because we have been actually working on this project. And Virtual Observatory India is some of the work that Persistent has done. And you may want to take a look at it. And this is all from that same research group that we've been working with. And so they came up with these SkyServers and Virtual Observatory. And this project has been going on now for the last 15 years or so. And, as he mentioned, this has been influenced very heavily by the research that Jim Gray did. And then he came up with Sky Query, saying, how do I federate all this database? And one thing though, he's very SQL centric. So everything that they do is all in SQL. He figured he's been writing that. He has, there's another, so he went beyond the astronomy guys to ecosystem sensors, oceanography people, and a whole bunch of other guys like that. And they all have been collecting data and putting it together and saying, what does it mean to share data between various sciences, and are there commonalities and a whole bunch of things around that. And this is post Jim Gray era. We've been working on a project called SciDB, which is the scientific database project, where what they did was they went to the hardest science problems guys and said, give us your most obnoxious 20 queries each. So everyone gave their queries and data problems, and then they've been trying to design what is the best database architecture for a system that can handle these kinds of scientific problems. Okay, so that's the other kind of thing that he did a lot of work on. So this is all relating to RNA, DNA, and I'm going to skip through this. But this is the work that he has continued to, has continued beyond him. There is an eScience award that is given every year to a researcher who works in this area. There's a conference that happens every year. Microsoft has been funding a workshop called the eScience Workshop. This is the link from the last workshop that I could track, which was in October 2012. So this is an area that continues to be fairly active. And a lot of the scientists have been really working on trying to integrate publications, data, and various other things. And in some sense, if you look at what people are talking about of integrating data and creating data as a service, in the scientific community, this concept is pretty much well accepted today. I just want to switch a bit to slightly different kinds of things. Again, he is an amazing guy and very prolific writer. And he wrote all the time. And he talks about this in his interview as well. He says that, I worked with a lot of stalwarts, but I was the one who was writing all the time. So none of the other guys wrote anything, but he wrote all the time. And he defined these two rules, that the person who types puts their name first, okay? And it's okay to not piss off anybody, so you can add other people on it. But the guy who did all the writing, he became the first author. So Gray is first author on many of the papers, and he attributes work to other people, but he's the one who became the spokesman and the main guy for a lot of the work that happened. So very prolific in his publications, meaning hundreds of publications, all fairly well articulated and available. He was a master presenter, and as I shared with you the videos, he had always this knack of trying to find the smoking, hairy golf ball kind of examples where all of a sudden people can look at complex concepts in this context of why do you need this golf ball, and why is it hairy, and why is it smoking? He was very much a community guy, and all the people who worked with him talk a lot about him being a very patient listener. I have had a few personal interactions with him in the mid-90s. His wife, Donna, used to work at Illustra, who was a customer of ours. Illustra, she was the documentation person there. So through her, she has introduced me to Jim as her husband. And of course, at various database conferences, he was at 95 VLDB, we were there. 94 VLDB, he was there. I tried inviting him to 96 VLDB in India, but somehow we couldn't get him here. So, definitely someone who always listened and was a kind of a low-key guy. He was not the most obnoxious, in the sense there were many other more obnoxious people in all the events. While this guy had content, he would be one who would listen and, say a few things which will always made sense. And then he actually mentored a lot of people, and this was a pretty nice article written by Ed Lazowska about the 500 special relationships Jim as a mentor to faculty and students. So he gives this list of things that a mentor needs to do. And while, I think it's a good thing to reflect on. So one of them is making time, simply listening, inspiring self-confidence, lighting the way, nurturing and pushing, following the muse, connecting good people and good ideas without boundaries, promoting the young, sharing knowledge selflessly, displaying professional integrity, advocating for the field, keeping things in perspective, and being a friend. So these are the properties of a mentor. So any of you looking to mentor, you should think about this. There is an article that I found from a Gong show where he talks about how to write a PhD thesis. And it's a 2-page thing in his own handwriting. It's kind of hard to read this, but he talks about, why you should do a PhD. Is it important? How do you pick a thesis topic? How do you go to advisors? How do you go about doing this whole thing? And since this was in his own handwriting, I thought this might be of relevance. So while Jim was doing very prolific work in the mid-2000s, 2006 and all that, he kind of was lost at sea on January 28, 2007. And what happened was his mother had expired, and he was supposedly taking her ashes to be dispersed at sea and along the San Francisco's northern coast in a ship. And he was a regular sailor, and he was sailing this ship called the Tenacious. And it was a fairly big sailboat. It's a 40 feet sailboat. So it's not a small canoe by any means, fairly big, equipped with all the latest equipment. And very surprisingly, it just vanished. So nobody could ever trace him. He went in the morning, and then nobody ever found him. And again, Gray was a very well-known person. He had a lot of friends and everyone else. So there was a massive search that happened so searching for Jim Gray itself was a big research project. A lot of people went online, and so they did, of course, they did the regular Coast Guard doing the, planes to the area to find where they can find him. But they got a whole bunch of satellite images from that period for a period of, 3 to 5 days, 10 days of satellite imagery. And they made that all available on the Mechanical Turk, which is the Amazon system, into small chunks. And they sort of asked for volunteers to go online and find out if you see the Tenacious in that small square. Actually, I also downloaded several hundred of those and kind of looked for them, yes, no, marked certain things. And they did this like crowdsourcing in a very big way around this thing. And again, a lot has been written about it. This is an article from Wired and another one from the Communications of the ACM. And then there were many papers written about this as well. But it's pretty amazing in terms of how they did this. Since he never, I guess nobody ever found him, nobody knew what happened to him. Did he die? What happened? Nobody knew. So they didn't know what whether to declare him dead or not dead or whatever. And then they had a tribute for his work on May 31st, 2008. Okay, almost 1.5 years later. And a lot of this is available on YouTube. And also in a Sigmod record. And many of his collaborators, one by one, came and talked about their interactions with Jim Gray from the early days, what happened in the IBM era, then how he worked with them in the tandem things, how he influenced them and all of that stuff. And some very phenomenal amount of, it's really interesting watching through those because it really gives a good glimpse of his personality. Again, this is the ship, or rather the boat. With this, I want to end today's session as far as I'm concerned. And I'd like to take any questions if there are any, but there is no shortage of literature. I would suggest if you do search on Jim Gray, Microsoft, that's a good place to start. Microsoft Research has a website dedicated to him with all the talks that he has done. There are about 75 to 80 different PowerPoint presentations there. Then he has several hundred papers which are all available online. He is cited all over the place very widely. Then there are videos of his work, oral testimony. He was on Sigmod records, wherever. Again, very well documented in terms of his history and pretty interesting, phenomenal work that he has done. So, this whole experience has been pretty exciting for me and quite overwhelming in some sense. So there's just a lot of stuff to read. If you have any questions, we can take them now. Can you check with the centers, please? Okay. Anybody else have any comments, any personal experiences of having worked with Jim?
And this is regarding the fourth paradigm, and it in some sense goes beyond Jim Gray, but like to have also your thoughts on the way we look at analytics. This concept that you are not going to presume in advance what relations you'll get, what correlations, what kind of models will come out, is actually a fundamental change, as he says. So is this something that Jim Gray actually was able to achieve through some of the work he did with the TerraServer or with the SkyServer? Interesting to know if in his lifetime he was able to actually come out with anything interesting through him, either himself or his collaborators.
No, I think some of the work that he did with SkyServer and all the astronomer work that he did was pretty much in his lifetime. Microsoft also had this SkyServer available on their website, and some of that happened while he was still around. So I'm pretty sure he was very much clued in terms of what was happening. What was missing though is that a lot of the work that he did was very SQL Server driven. So I don't think he really saw he was talking about everything relating to Hadoop, NoSQL, all of those things. But he never really talked about NoSQL, or nobody talked about NoSQL in 2006 and 2007 when he was the active researcher at that time. But having looked at some of the work, I think he may have had a much better reaction to some of this as compared to some of the other friends of his who pretty much had pretty nasty reactions to NoSQL in the early days. So if you look at the work, papers from Stonebreaker and Dewitt, they were, they pretty much, badmouthed these things. Though now, if you look at some of the Dewitt's work right now in the last 2 years, I think he has the best collection of Hadoop big data research papers, rather presentations today in the Microsoft conference that he has. The best, in my opinion, the best quality presentations on Hadoop and what exactly goes on in Hadoop and clusters today are from Dewitt. And 5 years back, if you see his papers, and again, I've heard Dewitt in many contexts, and we have, other people who know him well. Dewitt and Stonebreaker are not exactly, let me leave it at that. They have their own personality, and they can be pretty obnoxious, to say the least. And I've had personal interactions, including some view of their behavior in these kinds of situations. Gray was never like that. Gray was always if he didn't have good things to say, he wouldn't say much. Typically would kind of sit back and let it pass. That's not usually the case when you look at some of the other people in the field. Yes? You may have interacted with him, right, Naveen?
Yeah. So I do have a Jim Gray story to share. Please.
So I have a Jim Gray story to share. This is in the late 90s when I was working on my PhD. I was trying to build an extensible query optimizer for database systems, which could handle all the new data types, that new query languages that people are trying to build on top of RDBMS. And I was working with Divit. Divit was my advisor, and Divit considered Jim Gray to be one of his primary mentors.
Yes.
Right? So once Jim Gray was visiting Madison, and he was interested in my work. And so he actually scheduled a half day with me where he sat with me, he understood what I am doing, and he pretty much went through every line of my code. We sat with code in front of us, file after file, and he would ask, okay, what is this class? What does this do? What does that do? To date, Jim Gray is the only person who has looked at my code in this much detail. Okay? Not my colleagues who were sort of using my code and we were working together, not my advisor himself or anybody else. So Jim Gray is, he's so high up there, right? My advisor was considered one of the important people in his field, and Jim Gray is his mentor. And here is that guy is the only person to have actually sat and looked at code in this much level of detail.
No, I agreed. And a lot of other stories that you hear on the web and also talk about how young students, he has been very, you'd spend the time, like he gave you half a day and would go through the detail. A lot of other stories, personal stories like that on the web right now. Any other comment, question? Yes?
There was any collaboration or interaction between the two?
So question is between collaboration or interaction between Cord and Gray. See, in the early years of Gray's work when he was at IBM, I'm pretty sure Cord and Gray would have interacted, though I don't have any evidence of the same. That said, if you really look at what happened in the mid-70s, Cord did his relational database thing and kind of went on his own after that. So a lot of the papers that got written up in the System R team, which are all Pat Selinger, Irv Traeger, Bruce Lindsay, whole bunch of people, all stalwarts at that time. None of those papers include Cord in the list, but they're all Gray plus, there's like there are like 15 names in it, in all of these papers. And they have done pretty much all the phenomenal work around System R, which was the IBM's relational database. So Cord and Date to some extent were kind of off the chart and they did their own thingy. So I'm sure they were contemporaries, so they of course knew each other well, I would imagine, and had opinions about each other. I'm pretty sure. Anything else? So thanks a lot, and we'll take a tea break now, and we'll come back with Professor Trivedi.